Okay, this week we went to the track. We had some vibration problems. Got me thinking about shocks and what I've seen years ago and doing a limited amount of bleed and stuff like that. So I'm going to continue our shock series today, and let's talk about shocks. I've spent the last 30 plus years working on race cars, building race cars, and racing cars. And I'm here to help you better understand racing technology. Okay, I think there's a bunch of things I want to cover this week on shocks. This week I think we're going to get into digressive pistons and limiting the amount of bleed with digressive pistons, almost getting rid of the bleed totally or getting rid of the bleed. I'll show you exactly how a lot of digressive pistons are different and how they have a preloads preset into the cover plate. I also want to go over shock histograms and wheel histograms at different tracks. I want to define what shock histograms are and what they're used for and some interesting stuff with that. This is all stuff that you're probably not going to actually get data for unless you're out testing with a DataAct system. But it's good to know, and it's good to get you thinking about this stuff, even if you're not rebuilding your own shocks. It's kind of interesting stuff. I think the third thing I'd like to cover also is high frequency piston. This was big years ago with the Olin stuff. I don't really know. The TTX stuff is a lot different that Olin's is running now. But a high frequency piston, I'll describe what it is, how it works, and I guess we're going to get in when we're getting into the shock histograms. I'll have to describe frequency and amplitude in tracks and how I kind of think about tracks and separate them into the two different courses. First thing I want to describe is what a shock histogram is. And to really get into that, I think you're going to have to kind of understand frequencies. I had said in a previous video that most of your time is spent at 0 inches a second because your shaft is continually stopping and then getting moving again. So 0 point is probably going to be the most used portion of a shock histogram. What a shock histogram is, it's actually a measurement and a charting of how many times a shock spends at each inch per second. You'll have your compression side and your rebound side on how long they average out. And I'll do a diagram for it later and we'll get into that a little bit more. And it all has to go back with frequencies. And this also has to pair with either how we look at shocks as a digressive, a progressive, or a linear. The Formula One engineer that I went and took a class on said he didn't quite understand it yet. He was just starting to work on it, and this was mid-2000s, so I'm sure he figured it out by now. But he was saying that there's some sort of an alignment and traction by figuring out your shock histogram for a particular track and then trying to match the shock valvings to that histogram. It's kind of interesting. We'll go into it at a very light level because I'm not even that deep on the subject. So we're going to go into what he explained to me, and everybody can take it from there and think about it themselves. The second thing I want to talk about is digressive pistons. And these are really interesting if you really get thinking about how they work. There is a preload built into the cover plate shim of most digressive pistons that I've worked on. And you can actually eliminate bleed and put a very soft cover plate in there and stack it up, and you can get it so at least there's no initial bleed to take I guess make it feel sloppy or take a vibration out. You always want, I think, a little bit of a dampening there somehow. I'll draw you a diagram on what a digressive piston kind of looks like and what they do with that, I guess, that preload in there. The last thing I want to talk about today, and they were all the rage years ago, is a high frequency piston. The first time I had ever heard about it, Olin's had it. And what it is a little floating O-ring in there with some bleed holes. And it's supposed to take out at the very high end. As your piston changes direction, there's a certain amount of stiction to everything in there, to your piston band and everything. And that little bit of friction, they say at a high frequency, is enough to take traction out. So what they did is Olin's came up with a system. I'm pretty sure it's all patented. That's why the other shock companies that tried to copy them had to alter it and do a little something different. What it is where your piston band goes is an O-ring in there with some bleed holes that go towards the O-ring. And then your piston band goes over the outside. But what happens is when that thing goes to change directions, oil goes into the bleed holes, bleeds past that O-ring until the O-ring just moves up enough to block off that other set of holes in there. There's a set of holes on the top and on the bottom and a separating O-ring in there. And the O-ring flops between the two, and at a certain point in between the two, it lets the bleed go, so you get a high frequency, I guess, transition to it. But then it blocks it off and it operates as a normal piston. It's a pretty cool deal, and we had a lot of luck for many years running the high frequency stuff all the way around. Some people ran them just on like the rears, some people just ran them on three corners, right front, right rear, and left rear. We ran them on all four corners. And I'll go through and I'll draw a better diagram on how the high frequency stuff actually works. There are actually several different ways you can describe tracks and break them up into different categories. I got a couple different methods I use when I look at a track. And first method, which I won't go into too much because we're going to talk about frequency and stuff here, but I break up a track into either short radius or long radius. Long radius corners are those big sweeping corners that you don't lift much. If you do lift, it's a roll and you're right back with it, and you're actually turning through the radius of the corner. And then I describe them as short radius also. It's almost like a paperclip track. You drive in, you turn the car, and you drive out. Maybe there's a little bit of a turning transition, kind of a smooth turning now. The way we're setting up cars now is they're all getting a little bit more towards the large radius type of mindset. But years ago, when you'd run a paper clip track, especially like the swing arm Rayburn stuff with a ton of traction, you could get in there and turn that car real hard and drive right off the corner, and it was your typical diamond shaping or paperclip style track. The other way you can look at a track is high frequency and low frequency, and high amplitude and low amplitude. But usually your high frequency stuff is your black, slick, smooth, or tracks that are really cleaned up. And your low frequency, high amplitude tracks are stuff that is super rough, that you probably don't even want to run a car at, or it's real chunky and rough, and the bumps are big but they're further apart. A high frequency track, the bumps are smaller but they're closer together. So I guess with that being said, let's head over to the drawing board and let's get looking at some different drawings of a shock histogram, a digressive piston, and a high frequency piston. Okay, the first thing I want to describe, basically to get everybody all on the same page, is amplitude and frequency. If you've had trig in school, you probably already know this stuff. But basically, amplitude, if this is a wave, amplitude is the height of the wave, and frequency is the distance between the wave bumps. In a racing application, think of this as suspension motion or shock motion. This would be your rebound phase, shock going out, and this would be your compression phase, shock going in. So basically, like I said, with the two different types of tracks, you have your high amplitude, low frequency stuff, which actually equates to like a real rough track. If you want to describe it, as some people say, they're cornfields and stuff like that. Big bumps, but not many of them. A high frequency track would be your black slick stuff. It has very low amplitude. The tire doesn't move much, but yet it changes direction a lot. Whereas the high amplitude stuff, low frequency, probably doesn't change direction as much, but the bumps are bigger. And really, if you think about it, if you want to get traction with a shock absorber and a spring setup, you kind of want to take these things into two different groups. Next thing I want to talk about is a shock histogram. As this thing changes direction, we were talking before how the most common place it's going to be is probably 0, especially at your high frequency stuff, because it changes direction, the shock comes to a complete stop, and then changes direction again. So at the top and the bottom, at each cycle, your shock would end up at 0 inches per second, right? And then it would actually, this would be the fastest right here, and then it would start slowing down, and then it would start going up again. So if you chart all this and you have data acquisition, you take a lap around the track and you watch your shock paths in data acquisition, you can make a chart like this. And like I said, most of the time your shock will end up at 0 inches per second. So that would be your tallest. This is the amount of time. The height is the amount of time spent at each inch per second. One side would be compression, one side would be rebound. Then you go at your 1 inch per second, your 2 inch per second, all the way up. That Formula One engineer said he started going through histograms like this, and no matter what track they went to, he started noticing a pattern. And he hadn't put all the math together. He was a big math guy, and he hadn't put all the math together yet on how this all equates. But he said there is something here. And this, if you look at it, is actually kind of like a progressive shock stroker, shock valving. If you took this and you like turned it on its side, he said, that would almost be like a progressive shock valving. So he said there's something there to having a progressive valving. And at the time, this is the mid-2000s, everybody was either linear or digressive. There was some progressive thinking out in the dirt track market, but not a whole lot. Everybody was stuck on either linear or digressive. This is why I believe that if I were still into building shocks and experimenting heavily with shocks, I would be thinking towards this a little bit more. There's going to be some test and tune here because it's a totally foreign market, but just keep an eye on this and keep this in the back of your mind for a little while. I think in the future we're going to see stuff go like this a little bit more. The last thing I want to talk about is two different types of pistons. One's a digressive piston and one's a high frequency. When we were having some problems with vibration this last weekend, it got the gears turning. There was a large patch of rough on the bottom with some traction. That was probably a good place to be. But then when you got into the middle, it was black slick, typical dirt track deal. Traction on the bottom, traction maybe on the top, run through the black in the middle. And it got me really thinking about bleeds, and maybe bleed isn't so good, especially when you're getting bleed on a canister and stuff like that. It might even be something to experiment with back with a digressive piston. This is your typical digressive piston. Your cover plate would seal on this ring here. Right here. Your cover plate would be on there, and that would be your sealing ring. Your oil would flow in through here. On the opposite side, you'd have ports just like this underneath your cover plate. And they would be, if you drew a little dotted line here, it would be right underneath there. And your oil would flow in here and flow up against your cover plate on the opposite side, and your cover plate would seal all that up. What you can do on a digressive piston then is put bleed in there using a bleed disc. So I was thinking about what happens if you put a soft cover plate on there and then you stacked it up and made almost like a progressive valve stack, so as the shock gained speed, you'd still get the control you need, but yet you wouldn't have all that sloppy bleed in there to begin with. Another thing that's interesting with a lot of digressive shocks is that there is a amount of preload built in to the cover plate. This is where your shock shaft goes in the side view here. It will actually bolt up, and when you put your cover plate on there and you bolt it all down, your cover plate will actually end up a little bit drooped, because this portion here is just slightly lower than your cover plate deal, your cover plate stops or your mounts. So this will preload your cover plate. And you stack all that up and you pinch it all together. But now this isn't a tuning tool. This is an adjustment. So you could take shims, put them in here so there would be no preload, they call it, on the cover plate, or you can have a lot of preload on the cover plate. So what happens if you didn't put any shim in there, or any bleed in there, any bleed shim, and you put a shim underneath here to take almost all of the preload out of that cover plate, and then so you'd still have, maybe you'd have a little bit of preload just to give it some tension, but with no bleed and a thin shim, this would open up almost like bleed, but it wouldn't be as sloppy. You'd have at least a little bit control at the top and bottom. As we were looking at shock diagrams last week and shock dyno graphs, that would be if your dyno graph was actually kind of smoothed out on top instead of so pointed. Pointed deals probably are a little stiffer there. When they get kind of rounded out, they'll have a little bit of a control rate built into the compression and the rebound. I don't know now if it's really got a lot of bleed, it will be like way too sloppy, but you'd still want a little bit of control at the top and the bottom without putting bleed in there. I think there's something there. The other thing I wanted to talk about is a high frequency piston. I drew a little diagram here. These were little bleed orifices here, and they went from the top and the bottom, and this O-ring was smaller than the slot it sat in. So as this piston would go down, up and down at a high frequency track, similar to this, you know, it's traveling with a lot of frequency in it. Tires changing directions a lot, and the stretch is coming out of the tire, and it has a potential of losing traction. We learned about this before with tires. Anytime that stretch comes out of a tire, you're giving up a little bit of a traction. You always want that tire folded and stretched, and to do all your metering with your shocks. So what Öhlins did is they have little bleed orifices here, and as your shock is changing direction, this O-ring would flop, and the distance here that this O-ring would flop was to take out the high frequency bind and give a little bit of bleed, but then it would flop up against the and close off the holes at the top, or flop down and close off the holes against the bottom. And it would give just enough of that high frequency to give enough of a bleed to keep your traction in your tire and your tire stretched, but yet you didn't have to sacrifice lots of bleed or lots of control. High frequency pistons are awesome. I know we used them for years. I don't know, like I said, Öhlins I think is big on their TTX style shock now, but years ago with a standard style piston, the high frequency stuff was the way to go. If you liked this video and you thought it was pretty good information, subscribe to the channel below, and if you ring the bell, you will get a notification whenever I upload more videos. This will help me out, this will help the channel out, and it'll kind of give me an indication that people are really liking the content and I should probably keep going on this path. So subscribe and ring the bell, and we'll see you in the next video.